Hi, everybody. Today we're going to get into the topic you see at the top of the screen. We're going to talk about the inverse of a function. Now, I don't know whether you necessarily need to copy this out in your notes. We have a lesson handout for today that we're going to go through in detail. But to kind of give us a little introduction to that handout, you may want to jot down some of the stuff you see on your screen now. We're going to introduce the inverse of a function, and all an inverse is another change in the graph. It's important for us to note that we won't be examining an inverse in combination with what we've already talked about. So we don't have to worry about dealing with a vertical stretch by a factor of 2 and then shifted to the left 3 and then an inverse. No, that what we're going to examine is unto itself. Today, our inverse is like an isolated change in a graph or a function. So, what is an inverse? Well, if you see in red, really, when we take the inverse of a function, all we're really doing is just like reversing the function. Like we want to look at it, but from a different perspective, almost like the opposite perspective. So, as an example, you see I've put up our good old parabola. There's our y equals x squared. And if we were to talk in terms of what does that mean for input and output, x values and y values, we should know what we see in blue, that the outcome is always the square of the input. So my y values are always the square of my x's. And we see that explicitly in the equation. Y equals x squared. Y is x squared. So what does that mean for an inverse then? Well, it means we have to take the opposite direction. So we have to reverse our operation. So instead, our y values are now the square roots of the x values. Our original function, the y's were the squares of the x's. Our inverse, the y's are the square root of the x's. Okay, what does that mean in terms of our coordinates? Well, you see that I've just kind of put like a smattering of points that would lie on our basic parabola. If we were to then take the inverse, now what that means is my y is the square root of my x's. So if I happen to take like an x value of 4, then my y value would become the square root of that. So for instance, I could have 2 or I could have -2. And I'm going to actually just jot down both of those as their distinct points. Okay, I take a look. Now I've got my x value of 1 could end up with a square root of 1, which is 1, or -1, and we see both of those. If I jump to my next point, maybe I go all the way down to 3, 9. Well, if my x value was 3, so now I need that to be 9, well, the square root of 9 would be 3, or -3, and so on and so on. That maybe we can see a little pattern in our points. I'm going to just circle some of those points now so that we can maybe see a little bit of a pattern. I'm hoping that we can see that our coordinates, when we take an inverse, are swapped. We would technically say they're interchanged. And so if it makes a little bit of sense that what we're going to do is we're going to look at it from the different perspective, then really what was dependent is now independent, and what was independent is now dependent. We're interchanging our x and our y's. Okay, that was just a little bit of an intro, not so quick, but a little bit of an intro for us to jump into our lesson for today. So what I want you to do is make sure you have that handout, our lesson handout ready, and we're going to work our way through. Okay, here we go. Okay, so what you see then is now we're jumping into our handout. We've got a little bit of an introduction at the top. We're going to use this first page to knock out what we just spoke about on that previous screen. So this is why I said, I don't know if you need to get it down. We're going to get it down explicitly, and then we're going to add to it. So take a look at the top. Again, we're not just going to blindly copy down what's in color. We've been making changes to the equation of a graph, and that resulted in a change in its graph. One other relationship that we can examine is the inverse of a function, and we just noticed that we can do that by interchanging our x and our y. So what we are going to do is we're going to walk through the process of dealing with an inverse and then all of the quirks and things that we need to consider when doing so. The first thing that we need to make sure of is that we have our notation for it. So when we use function notation, we may name a function like f of x. If we were to name it f of x, then we have a label for what its inverse would look like so that we can relate it back to the original graph. So when it's inverse of the function, then we have that red notation. Now, I honestly wish that there was a better notation for inverse because a lot of us are almost going to view that little -1 up there as if it was like the exponent -1. It's not an exponent. It's a notation. So we would simply read that as your inverse of f. Okay, now we know how to express what the inverse looks like. We have the notation for it. Let's jump through a really basic example and we'll be able to get down some of that theory. So you see in the next portion, we're going to walk through example 1, I've called it. I've given you a base function, and you can see your base function. We are talking about f of x equals x plus 3. There's your good old line. Now, we take a look at that. It's written with function notation. For us to go through and deal with the inverse, what we really want to do is put the y back in. So we're going to change the equation of the function to be very generic. And you see that in red. Your y equals x plus 3. Okay, I want us to get down step by step how we find an inverse. It's not difficult whatsoever. It's just methodical. The first thing we need to do is interchange our x and our y. So I swap them out. That's going to give me this new equation. Can we make sure that we get that down almost as like step-by-step instructions? The first step is interchange x and y. Now what we want to do is we want to express that in a certain form. So everything we're going to do after that is to solve for y. So let's get the y all by itself. Well, we should be pretty quick to be able to get to y equals x minus 3. And so what we can do then is we can label that now as an inverse. So notice it is a function, so I can use my function notation, and we mark that as the inverse of f. And it was x minus 3. There we go. Okay, pretty straightforward, especially when we're dealing with a line. Now, what I want to do is I want to take a look at the graphical side of this. So what we're going to do is we're going to jump into like the second half of this front page. What we see is I've just given you 2 tables of values. Now I've turned the tables on their sides just to kind of save some space a little bit. So you'll notice that I've given you pretty generic x values in each of those tables, -2, -1, 0, 1, and 2. What I want you to do is fill in that number 1 spot, our original function, f of x. And then in the number 2 spot, let's fill in its inverse. And what I'd like to do is just go as fast as you can go and complete your table of values. Okay, so you fill in both of those tables of values, subbing in your x, calculating your y. Okay, pause it now. Okay, we're back. So if I was to match up with colors, then if I sub in a -2 in for x, I should get 1. If I sub in a -1, I should get 2. If I sub in 0, and so on and so on. If I do the same thing in my inverse and I sub in a -2, then I'm going to get -5, my -4, and so on and so on. Now, I'm not saying that there is anything super explicit in that table. However, we talked on the first screen about us going through and interchanging our x and our y. What was independent, dependent, dependent, independent. And maybe we can see that like pop up on our screen a little bit. If I was to zero in on an x value of -2, then I might say, well, in the inverse, can you see a y value of -2? And we do. Notice what your other coordinate was. It's 1s. So I'm just going to get rid of all those circles and arrows, and we may notice that the point -2, 1 has a matching point with interchanged coordinates on the other function. Well, let's see if that pattern continues. Well, I see an x value of -1. There's a y value of -1, and notice they've got the same other coordinate. So this point of -1, 2 may have become my 2, -1. Now, when we take a look at that in our table, that's about all we get to see. But if I was to extend that second table and say that I made it a little bit longer, because then I was able to go through and maybe sub in a value of 3. Well, if I sub in a 3, I'm going to get 0. And notice, we match up. There's my coordinates interchanged. If I was to sub in a 4, I'm going to get 1. Take a look. And so on and so on. That we should be pretty good then to be able to notice in that table that our coordinates, and we can just write down pretty quickly, they are interchanged. Now, that shouldn't surprise us so much. To create the inverse, we interchanged our x and our y. We swapped them out. So therefore, when we see our points, our set of ordered pairs, our coordinates, we also see those interchanged. Shouldn't be too shocking. Okay, what I want to do now is I want to focus in on the graph because I think we might see something interesting. So on the bottom of that page, I'm going to give you a moment just to get down your original function. So there is your f of x. You'll see that on the screen. It's our good old line with a y-intercept of 3 and a slope of 1. So pause it now, get that down. Okay, we're back. So now what we want to do is let's go ahead and put our inverse on that grid as well. So we have a y-intercept of -3 and a slope of 1. So over 1, up 1, over 1, up 1, over 1, up, and so on and so on. Now I go ahead and I connect all of those points in the pattern that it seems to represent. And I'm going to take great care in a straight edge, and I get down to something like that. That red line then would be the inverse of f. Now, I've given a little bit of a hint away on that right side when I said this graph represents a reflection. So I'm giving it away to you. It's actually a reflection that we get that red line by reflecting the blue line. I just want you to notice that we're not going to get it by reflecting it across the x-axis. And we're not going to get it by reflecting it across the y-axis. So there must be a different line that we are reflecting that in. Okay, if I can get everybody to put on their good old 45-degree line that passes through our origin, but all we're going to do is we're going to put on a dotted line. And that is our good old y equals x. Then maybe we can see that if I was to reflect my blue across that green line, it's going to give me my red. I can confirm that because I notice that everywhere on the other side of that green line, my blue line and red line are equidistant, the same distance away. Okay, there we go. We now have our reflection, and we can interpret the result of an inverse graphically. It has to be a reflection in the line y equals x. Now, I totally get that when we look back at that picture does not look proper because we have that dotted line and we may mistake that dotted line as like an asymptote. However, we're good to just make a note that that is our reflection line for today. Okay, let's turn over the page. Okay, I would like to go through just another mechanical process to make sure that we are good. This is such an algorithm for us that I want to make sure we are pretty automatic with it. Okay, let's go through and find the vertex of f of x equals 1/2 x plus 3. We might just notice a couple things that pop up algebraically. So our first step, rewrite your function by putting your y in there. We know that we have to interchange our x and our y, so I need our y in. Now that we have that, then let's interchange our x and our y. And everything else we're going to do is about solving for y. So everything else is about getting the y all by itself. Now, in order to do that, I need to get my y term all by itself. So let's get rid of that plus 3. Okay, now I have to get rid of that multiply by 1/2 out in front. So that means I have to divide by 1/2. Or if we can view that fraction as simply a divide by 2, then I need to get rid of that, so I need to multiply by 2. Notice in either case, multiplying by 2 or dividing by 1/2 is going to look the same. Okay, now what we can do is just simplify our function. So let's expand those brackets and simplify. Is that a function? Yep. So let's go ahead and let's write that then with our function notation as the inverse of f. Okay, there is our mechanical process. Same thing over and over again. So down below, we just have a quick, is the inverse of f the correct inverse? We don't know yet. Like we think we do. But let's get a little confirmation on our graph. So I'm going to get rid of that question mark because what we're going to do is we're going to very quickly graph both of those functions. So in blue, I'm going to graph y equals 1/2 x plus 3. And in orange, I'm going to graph the inverse of f, 2x minus 6. Okay, I would like you to go ahead and graph both of those lines as fast as you can. Okay, pause the video now. Okay, we're back. So pretty quickly, we should have been good to go y-intercept of 3 on my original graph. Slope of 1/2 means I go across 2 units, up 1, across 2, up 1, or back 2, down 1. However you want to deal with it. We should then be able to go through and connect those and produce our line. I'm going to be as accurate as I can be. And there is my line. That is my original f function. Okay, now I could do the same thing in the orange. I have a y-intercept at -6. I get down to there, but now I have a slope of 2, so I'm over 1 up 2, over 1 up 2, and I can connect those and extend that the width of my grid. And there is my inverse of f. Okay, so now can I answer the question, is that inverse the correct inverse? And I should be able to answer with a big, confident yes. Okay, why can I answer it that way? Well, if we recall from the last page, I know that when I find the inverse, my graph is a reflection in the line y equals x. And so if I just put on my reflection line, then there is my line, y equals x. I will notice that my blue graph is equidistant from that red line as what my orange graph is. That I might be a certain number of units there, I'm certain number of... Well, I also get a little confirmation. Look at where my invariant point is. I know that any points that are on the line of reflection will be invariant. And notice, I cross right at that point. Like if I wanted to specifically talk about that point would be at 6, 6. And we should be able to now kind of put together an idea. It should make sense that any point that has the same x and y coordinate will be unchanged for the inverse, because if I swap those points, I get the same graph. So how can we tell? Well, we can tell because it is a reflection in the line y equals x. And there we go. Okay, I think we've gone through a bunch of introduction now. What I want to do is I want to spend almost the rest of today going through and dealing with algebraically finding an inverse and graphically dealing with the inverse. We're going to find that as we start to get into more complex functions, there's going to be a few more things for us to consider. So let's jump into the bottom of the page. Okay, so let's jump into problem 1 then. Notice I've asked you to determine the inverse of each function, and then we're going to ask this kind of second question, and we'll kind of come back to this within each problem. We want to examine, is the inverse a function as well? So I want to jump into A and just make sure that we're good to be able to tackle that first one. So let's mechanically go through and find our inverse. So what I would like you to do, pause the video and go through algebraically and find the inverse of f. Okay, pause it now. Okay, we're back. So pretty quickly, we should have been able to go through and replace our f with our y, put it in there, interchange x and y. Now we need to isolate our y. So for us, we may have written it like this. However, I think for us to produce the graph, we may actually like it that way a little bit better. So I just want us to be conscious that on this line, you are perfect. You have your y completely isolated. Okay, we're going to now answer the purple question. Is the inverse a function as well? We take a look at the blue and we notice that it is a function because it's just another line. And therefore, we are going to use our function notation to denote that. There we go. Nice. Okay, what I want us to do is very, very quickly, let's put on the graph of each one of those. The original function f and the inverse of f. Okay, pause it now. Okay, we should be good. I'm going to go through and put on my original in red. So there is my y-intercept of 3 and a slope of 5. So I've got to go back 1 and then down 5. Back 1, down 5. And that gets me to that, and then I should be good to be able to connect those, extend it the length of the grid or the size of the grid. And I know that it's going off forever in both directions. There is f. Okay, now I can go ahead and I can put on the inverse of f. Now, I've got a y-intercept of negative 3/5, so that's like a negative 0.6. So I've got to estimate that a little bit. That one's going to be a little tougher because of my estimation. I'm a little bit past halfway. From there, I have a slope of 1/5. So I can go over 5 units and then up 1 unit. So maybe I'm there, or maybe I'm back 5 units. And down a unit. Something like that. I made my points a little smaller so that I could try to estimate better since I wasn't on the exact intersection of grid lines. Now I'm going to connect that. And I get something like that. And that is now my inverse of f. I have a little confirmation that if I go and I put on that corner to corner, my perfect 45-degree line, that I see I do intersect on the line y equals x. Nice. Okay, there we go. I would act as if A was just a bit of a review problem. Like partway through, do we have an idea of what's going on? Okay, I'm going to put a little wavy line down here. And what we're going to do is we're going to jump in and play around with B. So let's follow the exact same process. We're going to start off and we're going to algebraically find our inverse. So what I'd like you to do, pause the video now, find the inverse. Okay, we're back. So we should have been good, and I'm going to find my inverse in blue, replace your f of x with a y, interchange your x and your y. Now get your y all by itself. So to get that y all by itself, I have to get rid of my squared, which means I take the square root. And anytime I take the square root, I could have a plus or a minus as my solution. I just don't like the way that that x looks. So I'm just going to clean up that x a little bit. There we go. Okay. We should be pretty good then to be able to answer the question, is the function or the inverse a function as well? And we should get a pretty big no to that question. We can see that it's not because of that plus or minus out in front of my root. That when I sub in an x value, I'm going to get two y values, the positive and the negative case. That means that I will not label that inverse with my inverse notation. I just leave it as y equals. Okay, now what we want to do is we want to go ahead and we want to put on both of those graphs. So I'm going to ask you to pause it and put on the graph of the original and its inverse. Okay, pause it now. Okay, and we're back. So I should be able to go through and put on my original pretty quick. 2, 4, reflect that across the axis of symmetry. And now connect those with a smooth curve. Those will be the only points that I can put on this size grid. And I get something like that I can call F. Okay, now what I need to do, in blue, I'm going to put on y equals plus or minus root x. So the first thing I'm going to do is I'm going to put on y equals positive root x. That's my good old square root function, which I know goes through 0, 0, 1, 1, and 4, 2. Now I'm going to put on y equals negative root x, and I know that that is just my square root function reflected in the x-axis. So I'm now going to pass through those points, and I can connect those with a smooth curve, and there we go. Okay, we get a little extra confirmation that it's not a function because that blue curve would not pass the vertical line test. So what we end up getting is our parabola and then what kind of looks like a sideways parabola. Now, we have done everything that the question asked, but I'm going to change the question a little bit. That because we got down to this no problem, that the inverse was not a function, that we may be asked from time to time to go through and deal with maybe restricting our domain to ensure that the inverse is a function. Okay, what I want to do for that then is I want to go back and I actually want to examine our domain and our range. And I want us to see that in this instance, maybe we've got some extra information in there. So let's take a look at our original. And I'm going to put my original domain in red. That on that parabola, I could sub in anything for x, because I can square any number. My range is y must be greater than or equal to 0, because every time I square it, I'm going to get 0 or positive. We see it graphically. I'm going to put on the domain and the range, then, of my inverse. And what we'll notice is my domain is x must be greater than or equal to 0, and my range is that y can be anything. Now, I just want us to notice that our domain and our range are also interchanged. They're flipped. Now, it shouldn't be a big shock to us. However, we should be able to notice that the domain of one function, its x values, become the range of the other, and the range of one function becomes the domain of the other. So, important to make a point about that feature, that property of us finding inverses. Okay, so why is that important? Because if I was to ask you to restrict your domain in order to ensure that your inverse is a function, then we've got a couple options here. So, can we see what causes the problem? It's that, well, when I reflect that graph and I reflect it across the line y equals x, it goes sideways. So what I can do is I can just focus in on maybe like half of my parabola. So I just want you to take a look at the portion of my parabola that I'm going to highlight in orange. That right side of my parabola. Okay, I'm going to get rid of that highlight, and all I'm going to do is I'm going to kind of copy over that portion in green. Oops. There we go. That if I was to reflect that portion, then we should see that I should get this matching portion on my inverse. Now, how does that work out about restricting domain? It would be me instead saying that x cannot be everything on my original, but that x had to be greater than or 0, greater than or equal to 0. That would just give me the green portion on my original parabola. And we can now see that when we take the inverse, we're going to interchange that. That means my y value must be greater than or equal to 0 on my inverse, and I come right in on the green portion of my inverse. So notice, by restricting my domain on my original graph, I can ensure that my inverse is also a function. Okay, we could have done the exact same thing and just restricted it to the left side of the parabola, and that would have ensured that we got the bottom portion of the inverse. Either is acceptable. Okay, let's keep going with us dealing with some inverses. Let's flip over the page. So let's jump into problem C now. So tackle the same thing as what we did before. I want you to algebraically go through and find your inverse. Okay, pause it now. Okay, we're back. So this should be a pretty automatic process for us. However, there's the potential that maybe we made a little silly mistake here. We need to isolate our y term. And now, to get rid of the square root, I need to square. And we come in on that. Make sure that we're squaring the whole left side of that equation, not each individual term. Okay, we come in on that, and I'm hoping that we're pretty good. We may recognize a little issue. However, we should be pretty automatic to mark that as the inverse of g, because we recognize that that is a function, I would like to go through and produce the graphs together on this one. So I'm going to put my original in red. We should notice that it is our good old square root function shifted up 3 units. So my 0, 0 comes up at 0, 3, 1, 1 goes to 1, 4, and 4, 2 goes to 4, 5. And I now get that as my graph of G. Okay, well, I now go, and if I was to graph my blue, my inverse, I notice that that's my parabola, and it's been shifted to the right 3. So that puts my vertex at 3, 0, and now I would have 1, 1, 2, 4, those next kind of points, and then reflected across. I want you to notice that that's the graph of my inverse. And that is not the graphical inverse of the red line. So what was the problem? Well, we had something pop up here that hasn't popped up before. And I want us to take a look at our domain and range again, and I think we're going to find the problem. So I'm going to get rid of that blue parabola because I have a problem with it right now. I'm going to leave my points up. Okay. Up in purple, I'm going to talk about my domain and my range. So my domain and my range of my original graph. We should be good that our domain is x must be greater than or equal to 0. You see where the x is, or you're just looking at the picture. And our range is y must be greater than or equal to 3. Okay, if we now go and examine the domain and the range of my inverse, we may be tempted to say this. Because that is the inverse of the blue function. The problem is, that wasn't the domain and the range based on my original graph. So we're going to learn a little something new on this, that whatever my domain and my range are for my original function, that must also satisfy my inverse. So what am I talking about with that? Well, then that means that my domain of my original must become my range on my inverse. And so therefore, y must be greater than or equal to 0. Not much change on that. That still matches up. However, and I'm just going to get rid of that arrow, my range on my original curve then becomes my domain on my inverse. And you can see that we actually come up with what appears to be almost like a restricted domain. It's not. It's just that whatever my domain and range are for my original have to dictate where my inverse exists. I don't get to change where my inverse exists. And so when I take a look at those 5 points that I have down on my grid, I notice that 2 of those can't exist. This one can't, and up here cannot either. And I'm just going to kind of copy over that in red so we can see it disappear. That my parabola can only exist at 3 and greater. And maybe there we can see, okay, now that looks like the reflection across the line y equals x. Okay, now, there are different ways that you could tackle this. So what I'm going to do is just get rid of that curve again. And I want you to imagine that you went through and you put on those other points. Well, my suggestion to you would be almost like dot in your parabola that you see as your inverse, and then examine, okay, well, what should be the inverse based on my original graph, and then just make that part of your graph continuous. We're okay to leave that dotted point there as is. Our reader can see that it's just the red and the blue graph. Okay, if I put on my quick, very, very quick, 45-degree line through the origin, my y equals x, we'll get a little confirmation that we're invariant on that line. There we go. Okay, I think I added in a bunch of stuff for us now. That is, we can see how we can restrict the domain to ensure that our inverse is a function. That's not a focus for us. It just might be asked from time to time. But we can also see how the domain and the range of our original graph affect the domain and the range of our inverse. Okay, I'm going to leave you with D. I think D would be one of the uglier ones that I think you could algebraically find the inverse of. So what I'd like you to do is work your way through D and try to algebraically come up with the inverse. Okay, pause it now. Okay, we're back. So everything should be automatic. It's simply confirming. Get your x term all by itself, which means I first need to interchange my x and my y. Now, to get my y term all by itself, I have to get rid of that +1 on the end. Now, I need to get rid of that multiply by -1 out in front, which means I need to divide that out. Now, I'm going to write it that way because that just helps me to interpret my transformations later on. Now I have to get rid of my squared, which means take the square root. So my y plus 2 is going to equal the plus or minus square root of negative times x minus 1. Well, now the only thing left to do is let's get rid of the +2, and just for simplicity, I'm going to write that -2 on the end. Make sure that it is very clear that that -2 is not underneath your root. Okay, there we go. Now I'm going to leave it with you to go through and try to produce the sketch. I think this will probably be one of the more difficult ones for us today. I'm going to go through and put on my sketch of my original in red, and I'm going to put on my sketch of my inverse in blue. Okay, pause it now. Okay, we should be good. If we take a look at our red, I have my normal parabola that's been reflected across the x-axis, shifted to the left 2 and up 1. So take my vertex, shift it to the left 2, up 1. Take 1, 1, reflect it across, shift it left 2, up 1. I know that I have a reflection of that across the vertex. If I take 2, 4, and I reflect it across, shift it to the left 2 and up 1, then I come in on those points. I can reflect it across. Relatively quickly, I'm able to go through and produce something that looks like this. There is my F. Okay, now I need to graph the inverse of that. I can't label it as the inverse because it's clearly not a function. We've got plus or minus. So what I'm going to do is I'm going to graph the positive case of that function. So it is my good old square root function transformed. So I'm going to take that square root function, and now I'm going to take 0, 0, my first key point, and I'm going to reflect it across the x-axis, no change. Sorry, across the y-axis, no change. Shift it to the right 1, down 2. Now I'm going to take my point that would normally exist at 1, 1 and do all those transformations to it. Reflect it across the y-axis. Shift it to the right 1, down 2. Now I'm going to take, Now I'm going to take 4, 2, and perform those transformations. Reflected across the y-axis, right 1, down 2. I can now connect those points, knowing the shape of a square root function, and I get something like that. Now, we could go through that exact same thing, but now focus in on the negative of that case. So go back to your good old square root function, and now reflect across the x, then across the y, then to the right 1, then down 2. But if we are very, very confident with what we've put in blue, then we should be good that now what we need to do is almost reflect that across the line y equals 2. That we're going to get the matching other half of that parabola, that sideways parabola. So be okay to then say, well, I need to reflect that point across and that point across and generate your other side. Now, this is the only struggle with that, is that the only way I have the correct graph now is if I guaranteed that the first part of that was correct. I have no means to really check. Yes, I could go ahead and sub in a negative x value and confirm that I lie on that curve. But in terms of my transformations, I really don't have the same level of check. That if I was to then take, let's say, 4, 2, and now deal with the negative case. Reflect it across your x. Now reflect it across your y. Now shift it to the right 1, down 2. Now I would feel super confident because independently I got to that point. But the more practice we get, the less errors we make, we should feel pretty confident to simply sketch in or graph in that other half. Nice. Very good. Okay, we're almost done. Let's jump into the bottom of that page. Okay, what you see on your page right now is just a weird looking graph. I want you to notice it is a function, that it would pass the vertical line test. I'm going to argue that this problem, problem E, is probably the easiest one we've done all day. It just might not look that way right now. I'd like you to sketch the inverse of that function. So I want you to pause it and struggle your way through if it's a struggle. Okay, pause it now. Okay, we're back. Now, if there was anybody who was absolutely stumped on this one, then one of the things I might do is I might go back and locate my first key point. Like I noticed that I have that key point that's sitting in the location -5, -2. And I know that when I take an inverse for something, I know that that means that I interchange my coordinates. So my inverse would then have a point that would be at -2, -5. Okay, I think that might have caused a problem, solved the problem for anybody who is struggling through. I want you to pause it now and finish it off. Okay, we're back. So I'm just going to hammer through every single key point. I don't even have to write them down. My next key point is at -3, -2. So the inverse would be at -2, -3. I can connect them as I go. I want to draw your attention. Look at the interval between my key points in purple. It would be a horizontal line. Look at what happens to the inverse. It becomes vertical. Okay, that's a nice way to check. The inverse of horizontal become vertical. Okay, then I can keep going. Take my next key point, which is at -2, 2. That's going to get inverse to 2, -2. Now I can go ahead and take my point at 0, -1. That's going to get an inverse to -1, 0. That one shouldn't be a surprise for us. That when we take the inverse of a y-intercept, we're going to get an x-intercept. Because I'm interchanging the coordinates, then the one coordinate that was 0 means in its inverse, the other coordinate is 0. So x-intercepts become y-intercepts, y-intercepts become x-intercepts. My next key point, that is at 3, 5, is going to get transformed to 5, 3. And my last key point at 1, 2, 3, 4, 5, 6, 5 is going to get transformed to 5, 6. And now I should be good to be able to connect all of that stuff and confirm my picture. Now, a short while ago, somebody once told me after they produced this sketch that they saw something on there, and I swear now I can never look at that picture and not see it. One of my students told me that it looks like a frog. And I was like, shut up, it doesn't look like a frog. And now all I ever see is a frog after graphing that inverse. So I'm hoping that escapes your mind. Or it sticks in your mind, and now you remember how to go through and deal with an inverse of even an ugly graph. Hopefully E was pretty automatic. Okay, let's turn to our last page. I'd like us to go through then and find the inverse of our good old hyperbola. So let's work our way through that one. Okay, you should be good to be able to do it algebraically and graphically. So let's pause it now. Okay, we're back. So we plug in our y. We can now interchange our x and our y. And now we got to get the y all by itself. So you notice one of the problems is the y's on the denominator. So that means I have to get it off the denominator. So to get rid of a divide by y, I need to multiply by y. Now to get the y all by itself, I need to get rid of my times by x. So I'm going to divide by x. Oh. And you may have noticed something that popped up. That my inverse is the same as my original graph. Okay, does that gel with what I know about that original graph? Well, if I put my original on in blue, I know that I have a point at 1, 1, negative 1, 1, and I'm going to now have my branch that approaches both axes because we have our asymptotes there. And I would get the same thing in quadrant 3. Well, I just want us to take a look at that, and all I'm going to do is I'm going to put on that reflection line of y equals x. And I think that we should be good to see that, well, when I do reflect, I'm actually going to lie on the same position. So if I took part of the branch up in quadrant 1, and I reflect that across y equals x, then I'm going to get this green portion on that branch. But then the same thing, if I was to reflect the green portion, I'm going to get the red, and we can see the same thing takes place in quadrant 3. That when I reflect that hyperbola across y equals x, I get the exact same graph. What's really important for us to recognize is it doesn't mean the graph is invariant. No, not at all. Yes, this point that I'm going to circle in purple may be invariant, 1, 1. This point, negative 1, negative 1. But the rest of the graph is moving. The red portion of the branch becomes the green becomes the red. So I only have 2 invariant points, even though the whole graph looks like nothing changed. Okay, on the bottom of that page, I just snuck in one other question to just ask, can you think of any other relations where if you took the inverse of it, we would get the same graph? Well, a couple things that might come to mind. Let's go with like our most basic. Like, what about y equals x? Like, even look back up onto that grid. My orange line is y equals x. If I interchange, then I get x equals y. Those are the same function. Okay, could we think of anything else? Well, maybe y equals negative x. Picture y equals negative x. Now you're going to get that perfect 45-degree line, but with a slope of -1. We would be going in the opposite direction. If I were to reflect that across y equals x, I'm going to get the exact same graph. We can see it algebraically. Interchange your x and your y. Now get your y all by itself. Yep, same equation. In fact, if you were to take any line that had a slope of -1, we may find that that's going to give us the same picture. I'm just going to get rid of your hyperbola up top. You should be keeping yours on your page. But if I was to go through, and now let's just say put on the line y equals -x plus 2. Then that means I have a y-intercept at 2 and a slope of -1. So I'm going to have that perfect 45-degree line, but now I'm passing through a y-intercept of 2, not 0. That gives me that graph. Well, if I put on my good old 45-degree line, my line of reflection for my inverse, then you might see that if we were to reflect that blue line, we're going to get the blue line again. I'll leave it to you to look at that algebraically. Now, maybe one other thing popped into your head. He didn't say functions. The question said relations. And so maybe that word jumped out at you, that there's actually another type of relation that you have background with. It's not a function, but that you have background with that you might have thought of. I'm going to do my best to draw it in purple and not as a highlighter. What about our good old circle? If we consider a circle that's centered at 0, 0, and we reflect that across that line, we're going to get the exact same thing. One half of the circle reflects onto the other half and vice versa. That if we had our x squared plus y squared equals r squared from grade 10, that inverse actually is its inverse of itself. In fact, any circle that has as its center y equals x would be an inverse of itself. Okay, something just to look at the end then. Okay, that is everything for today. Today was a big day. Just remember that as we work our way through to deal with inverses, inverses are not going to be combined with our other transformations. So your job is to make sure that you are good to be able to sketch and graph a function based on your transformations, and then independently be good at being able to find an inverse. Okay, jump in, play around with your practice. You should be good. Okay, good luck.